Hello viewers, today we're going to prove e to the I pi equals -1 using the Maclaurin series. Now this may seem a very complicated process, but once you really knuckle down and start to understand the parts of it, it becomes quite simple. The Maclaurin series is an expansion series of a function, where the approximate value of a function is determined as the sum of the derivatives of the function. So we'll start off by understanding what the equation is. So it can be written as the sum of infinite terms where n starts as 1 so what this is n factorial, and that equals fx of 0 plus f dash 0 x to the power of 1 over 1 factorial. And you'll start to see a pattern develop here. So we can go f double dash, which is the derivative of the first term before that, x squared over 2 factorial plus f 3 dash x cubed over 3 factorial, and so on. Now this term actually gets more accurate as the number of terms increases. So for all intents and purposes, we're going to start with e to the fx equals e to the x. So we need to know what these terms are, so we're going to start off by figuring them out. So if we let e to the x equal fx, we can see that when f0 equals e to the 0, as you're subbing in 0, that equals 1, and we know that because it's quite simple maths. Then we write here the derivative of this equals e to the x. We know that the derivative of e to the x is just e to the x, and so on, and that doesn't change. So as we sub in 0 for this one, that equals 1, and we can also say that the double derivative equals e to the x, which means this also equals 1, and so on. So now what we can do is we can sub it into the Maclaurin series, and we can say that e to the x equals 1, subbing in this into here, and now we'll sub them into these ones, plus 1x to the power of 1 over 1 factorial, plus 1x squared over 2 factorial, plus 1x cubed over 3 factorial, and so on. It's pretty self-explanatory what goes on after that. And so now, once we've understood that, we can now let fx equal sine x, just to move this step further. So once we let fx equal sine x, we know that f0 equals 0, because on the unit circle, sine 0 equals 0. So then, using the same sequences as the step before, f dash x equals cos x, because the derivative of sine x is cos x. And there we can see that once you sub 0 onto that, it equals 1, because cos 1 equals cos 0 equals 1. And here we know that f double dash x equals negative sine x, using our simple derivatives. And then we can see that this is equal to this. And we'll go one more, we'll say f triple dash x equals negative cos x. And we can see that that is equal to -1, and so on. So once we use that, using the Maclaurin series, we can sub that into the equation, and we can say that sine x is equal to 0, subbing in the first one, and then we'll sub it into this to make you help understand. Plus x over 1 factorial, subbing into this term as f derivative of fx equals 1. And as the next term is 0, 0 times any number is 0, so it's just 0. And then we see here that it's f triple dash equals -1. So this is where we get minus x cubed over 3 factorial. And we see a pattern start to develop here. 0, 1, 0, negative 1, and so that just repeats itself. So that gives us plus 0 plus x to the 5 over 5 factorial plus 0, and so on. So it's really quite simple once you have what your variables are to sub them into the equation. So now once we've done that, I'm going to get a new page because we don't want to get messy here. We're going to let fx equal cos x. So letting fx equal cos x, we know that when f equals 0, that equals 1, because cos of 0 equals 1 using the unit circle. And using the same sequence as before, f dash x equals negative sine x, using your derivatives, and then f dash 0 is equal to 0. And then we'll do the same thing, f dash dash x equals negative cos x, and we can see that f dash dash of 0 equals negative 1. And one more, we will do triple dash, just for all intensive purposes. That is equal to sine x, as the derivative of negative cos x is sine x, and there we can see that subbing in 0, you will get 0. So the same as before, you can see a pattern starts developing, 1, 0, negative 1, 0. So that's helpful when we sub it into the Maclaurin series. So once we sub it into there, we can say cos x equals 1, as that's the first term, subbing into this one, plus 0, because 0 times any number is just 0. And then we can say, because that's negative 1, we get negative x squared over 2 factorial. And that goes on to be plus 0, as the next term is 0. So this pattern is quite helpful now, because now we can say that is plus x to the 4 over 4 factorial plus 0 minus x to the 6 over 6 factorial, and so on. So now that we understand the basis of that, now we can help understand this formula more easily. So this cos x and sin x will become very helpful later on when we actually start to understand this, because some magic will happen. So now's when we do something a bit different. What we're actually going to do is we're going to use the Maclaurin series, but we're going to use e to the ix. Now this may seem pretty complicated, but it's actually quite simple, because over here we have e to the x, and the only difference with e to the ix is wherever there's an x, we times it by an I. So we'll see what we can do here. We get that, it's just 1, now plus ix over 1 factorial. We just times it by an I because there's x here, and we're going to do the same thing for the next one. So that is multiplied by ix squared over 2 factorial plus ix cubed over 3 factorial plus ix to the 4 over 4 factorial, and so on. It's quite a simple process. Now we can actually try to simplify this, so we write e to the ix equals 1 plus ix, and this just becomes ix because 1 factorial is simply 1 plus ix, and now we have here I squared is negative 1. So we can write here, that's not a plus sign, that becomes a minus. So it is minus x squared over 2 factorial. And then here we have I cubed. Now I cubed is actually negative I, because I squared is negative 1 times I is negative I. So we have a minus here, so we can write negative ix cubed over 3 factorial. And now we can write this one as I to the 4, because I to the 4 is actually I squared times I squared. So that's negative 1 times negative 1. So that just becomes 1. So we can just write plus x to the 4 over 4 factorial, and so on. We can actually do one more here, just to make it a bit simple later on. So here we can write x plus x to the plus x to the 5 over 5 factorial. This is actually multiplied by an I here, because in this series it would be I to the 5. Now I to the 5 is I squared times I squared, which is 1 in the earlier one, times I. So we can see that that becomes a plus I. Now what we do next is we simplify them into real and imaginary terms. So this helps us understand the crux of the Euler's formula. So what we do here is we write this again, and we're going to simplify the real ones first. So 1 is a real number, so we can put that there. And anything that is a real number is something that there's no I with. So we can say here that this formula here is a real, so we write minus x squared over 2 factorial. And then we can see that this is also a real term, so we can write plus x to the 4 over 4 factorial. And all the rest remaining are imaginary terms. So we can factor out the I in the imaginary terms, as this one, and this one all have I's in them. So we're going to do that, and we can write x here, factoring out the I. And here we can write x cubed over 3 factorial. And then for this one here, it's very similar, except it's a plus, so it's x to the 5 over 5 factorial. Now, this is where the magic happens. So we can see here that this and this are very different, but they're also the same. So over here, when we worked out the cos, here's where we worked out the cos, we can see that this and this are very similar in a way that it's 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial, and so on. We would also get this if we continued to do a longer one in the e to the ix. So what we can do here is we can write this as cos x using the Maclaurin series, because that's what we found here, and that's cos x. And over here, you can probably have a guess what this is going to be, but it's very similar to this one in a way that x over 1 factorial equals x, and then it is also negative x cubed over 3 factorial, and so on. So what we can say here is this is equal to sine x. Now you may start to get goosebumps here, as this is quite mind-blowing, because what we can then write is e to the ix equals what we have here is cos x, and what we have here, don't forget the I, schoolboy error here, leaving out the I, plus I sine x. Now if we take this a step further to actually figure out the Euler's formula, what we do is we sub pi in for x. This makes it a bit tricky, but e to the I pi equals, now because we replace the x with the pi, we need to sub pi into here and here. So we get cos pi plus I sine pi. Now this is very basic trig, so we just write e to the I pi equals. Now using the unit circle here, we can see that pi is over here, and that is also negative 1. So we can write that as negative 1, and that is plus, we can see that sine of pi is 0. So we can write 0, and if that's 0, I multiplied by 0 equals 0. So now we can write that as e to the I pi equals negative 1. Now what we actually have done here, this is the Euler's formula. So starting with this, we have come to this, and this is the basic proof using the Maclaurin series of e to the I pi equals negative 1. Thanks for listening, and I hope I have helped you out with this video.